Good afternoon, everyone. Today, my topic is load balancing multiple LCD light field display. Firstly, let me introduce what is multiple LCD display. Multiple LCD layers are stacked which construct a special light modulator, and the light emitted from the backlight is modulated by the LCD layers. The light ray set produced by the LCD layers construct a light field. People in different positions will see different view images from different perspectives. Then they can get a 3D effect. Compared to the previous 3D display technology like volumetric display and projector array and lenticular lens or integral imaging, multiple LCD display require low mechanical motion and there is low image resolution loss. In addition, this technology can be implemented easily on the mobile devices. Well, there is two main disadvantages. The transmittance of LCD panel is very low, so more LCD layers will result in lower display brightness. And another challenging problem is how to decompose the huge target light field into limited LCD layers. In other words, we need to display the light field compressively. In this paper, we analyze the performance of light field decomposition by casting the problem as an overdetermined equation set. And we found the multiple LCD display is working in the state of serious overload. So we developed a multi-layer and multi-zone joint optimization strategy to solve this problem. And finally, we built a prototype to implement a real-time light field decomposition and a display based on multiple GPU cores. Before introducing light field display, let me give the definition of light field. Light field is an array of view images from different perspectives. And it should be noted that the number of view images is greatly larger than the number of LCD layers. That's why we called it compressive display. Each light ray can be projected back to all LCD panels, and we can find the intersection point with each LCD panel. The light ray can be expressed by the production of the 3 intersection pixels values, and we can also express the light rays by the summation of the 3 intersection pixels in the logarithmic field. Any one view image is produced by all LCD layers, but different view image is a combination of different pixels. If we can get the layer images, then we put the layer image to the corresponding LCD panel and layer C. And the light can be modulated. Then the light field can be reconstructed in front of the LCD screens. But the problem is how to improve the quality of the constructed light field. Well, to analyze the performance of light field decomposition, we built a simple, direct but effective model to analyze the processing of decomposition. We vectorize the high-dimension light field into a long vector, and we also rearrange the high-dimension light layers into a much shorter vector in the same way. Now the high-dimension light field and the high-dimension LCD layers can be connected by a 2D transform matrix. We think pixels in the LCD panels are controllable units, and we assume the target light field to the load needs to be solved. Well, it's obviously it's an overload equation set. Each controllable unit is responsible to modulate multiple light rays. In this case, the light field is 7 by 7, and there is only 3 LCD layers. The load on one pixel is 16 light rays. In other words, it's difficult for one pixel to give consideration to all 16 light rays. So there are 2 strategies to solve this problem. The strategy 1 is to increase LCD layers, then we can get more controllable units. And the strategy 2 is to reduce the load by resolving the light field spatially. We tested strategy 1 in 2 things, the core and the dice. We keep the size of light field in constant 7 by 7. And the LCD layers increases. And we can see the display quality improved at the beginning from 2 layers to 3 layers. But after 3 layers, the increased LCD layers make a limited contribution to improve light field quality. And the computation time cost increase linearly with the LCD layers. And most importantly, the display brightness will decreases considerably along with the increasing of LCD layers. This is a visualization of decomposition. From the results, we can see the parallax is reconstructed successfully, but there is some ghost and blurring. Maybe you can see the edge around the green dice. There is some ghost around the edge, and there is some blurring around the head of the car. Now let's pay attention to the strategy 2, load balancing decomposition. We use a directional backlight to replace the uniform backlight. The directional light rays is modulated by LCD layers, and the target light rays is divided into multiple subzones. And one time there is only one subzone is displayed, and the all 4 subzones is displayed in sequence. From the mathematical model, we can see in one time, only partial light field need to be decomposed and displayed. So the load on the 3 LCD layers is reduced significantly. And in other words, the 3 LCD layers is working in the time multiplexing. And again, this strategy without requiring extra LCD layers, so the display brightness keeping a high level. We also tested strategy 2 in the same things, the core and the dice, but we keep the LCD layers in constant 3 layers, and the size of light field decreases. From the results, we can see smaller light field size acquiring greatly quality improvement for constant LCD layers, and the computation time cost decreases by resolving the light field. In order to implement load balancing on GPUs, we developed an iterative algorithm to update the LCD layers. Our algorithm updates the LCD layers in update 1 layer at one time, and the rest of the layers keep fixed before finishing the updating current layers. We minimize the errors between the target light rays and the reconstructed light rays. By defaulting the derivative to be 0, we can get the update rulers for the first layers. We can see the updated pixels value is the production of the old pixel value and the weight factor. And the weight factor depends on the target light rays and the reconstructed light rays before updating, and also depends on the LCD, also depends on the pixel values on other LCD layers. Similarly, we can get the updated rulers for the second and the third layers. We use a 7x3 light field to test our load balancing decomposition algorithm. This is the original light field. We use 2 display cards. The model of display card is GeForce 6 lighting. And one display card has 2 GPU cores, so we have 4 GPU cores. And one GPU core is responsible to decompose a subzone of the light field. The table shows the display quality and the time cost. From the results, we can see the display quality is generally above than 13 dB, and the time cost is 13.3 milliseconds at most. So the light field can be displayed at 13 frames per second. By comparing the original light field and the reconstructed light field, we can see the parallax is reconstructed correctly, and the blurring and the ghost around the object is reduced. The left side is our prototype. The model of the LCD panel is ASUS VG278H, and this LCD panel can display the image and up to 114 frames per second. And we put a lenticular lens shed on the LCD panel, which near the backlight source. The right side is a photograph of the prototype in the indoor lighting environment. And the bottom is the photograph of the prototype in the front of the LCD screen from different perspectives. And we can see from different direction or from different position, we can get different images, and the parallax is correct. According to above discussion, we can conclude that the strategy of increasing LCD layers improve display quality slightly, but at the price of greatly decreased display brightness. Our load balancing optimizations improve display quality without actual LCD layers. So the display brightness keep a high level in the indoor lighting environment. And another advantage of the load balancing decomposition is this strategy further explores the spatial independence of the light field. So we can implement the algorithm on multi-GPUs. Thanks for your attention.
Okay.